Good evening. So today we're going to go over the basic concepts of the derivative and an integral of a vector function. Many of these calculus 3 concepts will be analogous actually to calculus 1 concepts, and I'm going to emphasize heavily all the time when this happens because it will help in understanding the new topics. We're going to also have to emphasize what's different, that goes without saying, but many of the principles are the same, and that's important to keep in mind to make it easy. So just a very brief recollection of the calculus 1 concept of a derivative. Very schematic, right? So I mean, if you have a single variable function, the whole idea of the derivative is to ask what is the rate of change of that function, the value of the function, if the variable of the function, the argument of the function changes a little bit, right? So if I look at a small change, let's say between a point x and x plus h, if you remember from calculus 1, h denotes a small change, small in the real analysis context, right? I mean, eventually that's going to be a limit as h goes to 0. But if I look at two nearby points on the domain, again denoted by x and x plus h, the question is, what is the difference between f of x and f of x plus h? What is the difference in the corresponding y coordinates as x changes? It's another fancy of asking what's the slope of the secant line. So slope secant line that connects the 2 points on the graph is nothing but what we call in calculus 1 the difference of a limit of it's the difference quotient of that function around those points, f of x plus h minus f of x over h. Okay, so that's the secant line. Now obviously as h goes to 0, if that limit exists, that leads to the concept of a derivative, right? Which visually is nothing but the slope of the tangent line. So as h goes to 0, we call that limit, if it exists, the derivative of the function at that point. And again, the immediate graphical interpretation of that limit is that this is the slope of the tangent line. So I want to emphasize that we're going to ask precisely the same type of question for a vector function. So let's take a vector function in R3. By the way, the definition for a derivative of a vector function in 2 dimensions is exactly the same, except you have only 2 components instead of 3. So let's suppose the components of these vector functions are a of t, b of t, c of t. And let's say this is our coordinate system. And the curve could be anything in space, right? A motion in space denoted by r of t, right? But let's make it kind of easier to follow. Just imagine that this is really a 3D curve, just so I can fit in nicely some of the elements I want to fit in the picture. So the domain is somewhere here, right? I mean, remember the domain is not usually plotted, but the same idea works here, okay? I mean, I'm looking at 2 nearby points on the domain, t and t plus h, and let's say the corresponding position vectors are over here, okay? So let's say r of t is over here, and r of t plus h is down here. So what can I say about the change in this position vector? Now think in terms of vectors, right? So I'm looking at r of t plus h minus r of t in comparison to the difference between t plus h and t, which is h. Now let's be careful for a moment here and let's see visually what this represents. On the top there's a difference of two vectors. Now think in terms of the vector addition. The difference of two vectors is just a particular case of vector addition, right? But anyway, if you remember how vector addition works, you should visualize that r of t plus h minus r of t is that green vector I showed there. It's the one that completes the triangle, right? So r of t plus the green vector gives me r of t plus h. So the difference of the two is the green vector. So I'm looking, when you look at the change of r of t, you're looking at the change in both magnitude and direction, obviously, right? Because the vector contains two important types of information, right? I mean, the magnitude and the direction. I also want to point out that this is an abuse of notation, this over h, because we didn't define anything resembling division of a vector by a scalar. Remember, on the top we have a vector, on the bottom we have a scalar. But this difference quotient, you can define it as 1 over h, the scalar 1 over h, scalar multiple the vector given by r of t plus h minus r of t. Now, I don't penalize, and I accept over h. We know what it means from context, but just in the name of precision, to make it clear, we don't have division to a scalar by a vector, right? It's a scalar multiplication to 1 over h. So, same idea like in calculus 1, what is this instantaneous change at the point t, right? I mean, if I focus on the point t, what is the limit as h goes to 0? This is what is going to give me, by definition, what we're going to call later r prime of t. So r prime of t is nothing but the limit of this difference quotient. And visually, just like in calculus 1, as h approaches 0 and these two vectors come close to each other, that r prime of t, it'll be basically this secant vector, it will become a tangent vector. Tangent vector to the curve at t, right, at the given point t. It's a local quantity, right? I mean, if you change the point, you have a different tangent vector, obviously. So I hope the analogy is pretty clear, right? In calculus 1, f prime of x is the slope of the tangent line. In calculus 3, r prime of t is the tangent vector at the curve. It will have its own magnitude and orientation, obviously. And remember always that by itself r prime of t indicates how both magnitude and direction of r of t changes at t, right? So it's the rate of change at t for both the direction and the magnitude. To go back with the analogy with motion analogy, if r of t is the displacement of the object, excuse me, if r of t is the position vector, you can think of r prime of t as the velocity vector. I don't want to call it displacement. Displacement is usually from two nearby points. You know, measures. Basically, it's going to be an integral, measures what the displacement from one point to another. So this is the position vector at time t of the particle. R prime of t is the velocity vector at that point in time. So that being the case, obviously, the magnitude of it is going to be the speed. Right? So if you only want to know how fast you're going, you're going to have to find the magnitude of r prime of t of the tangent vector. If you also want to know where you go, of course, you have to look at the direction of r prime of t. If you only care about the direction and not the magnitude, we'll get to that. That's going to be the that's going to lead to the concept of the unit tangent, which I'm going to talk about in a moment. But let's finish up the basics with the definition of the derivative. Now notice, if I look at the definition, so let's take this difference quotient a little bit further here. If I look at that difference quotient by components, r of t plus h minus r of t is the vector of components a of t plus h minus a of t, right? Just remember our components a of t, b of t, c of t. B of t plus h minus b of t, c of t plus h minus c of t. And then if we bring in 1 over h in a scalar multiplication, if all these difference quotients limit exists, notice that this is nothing but the old-fashioned derivatives, calculus 1 derivatives for each component. So computationally speaking, it's like it's almost nothing new actually in terms of what we learned so far. How do you differentiate a vector function? You differentiate each component at a time, right? So you differentiate each component, in other words. The concept of the derivative of a vector function translates to the concept of the derivative at each component function, right? So in short, r prime of t is a prime of t, b prime of t, c prime of t. Again, you need all these three to exist for this to make sense. All right, so with that in mind, we can go over a couple of examples already, and let's stay tuned for the next page. All right, so I want to go over a couple of examples in which the question is to sketch both r and r prime, both r of t and r prime of t, at the given point specified. Now notice, sometimes if there is no risk of confusion, we can just keep of t just to not write a lot of parentheses, but only if there is no risk of confusion, right? Just like we say in calculus 1 f or f prime and so on and so forth. And let's this time to actually use to do this sketch with two-dimensional vectors because it's easier, obviously. So let's suppose in our first example, let's say r of t is equal to t and t squared, and I want to sketch r of 1 and r prime of 1. Notice, just like in calculus 1, obviously you have to compute the derivative with respect to t first before you actually plug in any points, right? So r prime of t will be obviously 1 and 2t, and therefore r of 1 is going to be 1 and 1 if I plug in 1, and r prime of 1 is going to be 1, 2 times 1, so the vector 1, 2. We're not going to do a lot of sketching in this class by hand, but just to fix the basics of the concept here. So let's say you know, the curve is over here. Actually, the curve is easy to figure out. I'll get to that in a moment. And the point 1 is over here, so this is x and y. Remember, these are vectors in component form. So r of 1 is 1, 1, right? So that's pretty straightforward. This is r of 1. Let's say this is 1 over here. This is r of 1. Now, here's another remark here that we have to ponder a little bit. Normally, if you were to sketch, this is r prime of 1, right? Normally, if I were to sketch 1, 2, right, r prime of 1, which is the vector 1, 2, since it's in the component form, I should probably write it, you know, starting at the origin. But remember what I told you. Even though in computation we use vectors in the component form always represents a vector starting at the origin, if you remember. nothing stops you to actually show a representative of this vector in a different position where it makes more sense. So where does it make sense to place r prime of 1? Or, well, obviously at the point here in question where I computed the derivative, because that's where the tangent vector is located. So how do I sketch 1, 2? Well, 1, 2 in component form simply means that you move 1 unit to the right and 2 units upward. So measures, I'm not going to make a mess here and label it here, but just hear my words, right? So first component is 1 plus 1. That means over to the right 1 unit. Second component is 2, upward 2 units. So then in the right corner here, that's going to be the terminal point of the tangent vector. Let's do it with the red color here so I can emphasize it, right? So then this is like the curve. It's kind of squished there anyway. So that's the tangent vector 1, 2. I'm going to probably redraw this because I want to make a remark when I see this picture side by side. So let's do another example, very similar to this one. Let's say r of t is given by t squared and t fourth. And the same question, I want to compute and sketch r of 1 and r prime of 1. All right, so the derivative would be, in this case, 2t 4t third. And r of 1 again is 1, 1. And r prime of 1 is equal to 2, 4. And notice that, because I chose this example for a purpose here, notice that 2, 4 is actually a multiple of the previous one. A scalar multiple, which means these two are parallel, basically. So at this point, we're going to sketch them in a minute, but notice something else. Let's write it as a remark here. Notice that both these examples lie on the same curve. The reason is because let's take a look at the first example here. What is the relationship between x and y, right? So the x component is t, the y component is t squared. Now notice that if I eliminate t from the from x equals t, y equals t squared, that means that curve, that motion, in other words, lies on the curve y equals x squared. Remember, if you eliminate t, you basically compute or figure out the curve where this motion takes place. It goes over that parabola. In the second vector function, which is a different one, right? It's t squared t fourth, but notice the dependence of x and y is the same, right? If I square t squared, I get t fourth. So the second one lies on the same graph of a parabola. So what is the difference between them? So if I, again, side by side, sketch these two examples, right? So we have a parabola. Let's do it, write it like the dotted line like this. Position vector is the same for all of them. Okay, this is 1, 1, 1, 1. So in both cases, this is r of 1, and this is r of 1 as well. So what's the difference? Well, the tangent vector is different, right? In the first case, the tangent vector is going to be 1, 2. I'm not sure if I have enough room here so I can make my point. In the second case, the tangent vector is twice as long, right? So in the first case, r prime of 1 is 1, 2. R prime of 1 is 2, 4. So again, if we use this analogy with the motion, what I want to point out here is that really in both cases, the change in direction is the same, right? But the magnitude is different. The change in magnitude is bigger on the second example, right? This is my second example over here. So it's like you have two cases of a mobile going on the same path, but with different speeds. Right? The second one is faster than the previous one. So I make this, I mean, for most of you probably watching this, it's probably pretty obvious. So I mean, wonder why do I spend so much time with this? Again, to emphasize one more time that the tangent vector gives you both the change in direction and the change in the magnitude. But often you may want to know exactly if and how much only the direction changes, or if and how much only the magnitude changes. If I'm interested in the speed, of course, I'm looking at the magnitude of r prime of 1, right? If I want to figure out the speed, which is going to be different. But the direction, notice in this case, is the same, right? I mean, 1, 2, and 2, 4 are parallel. So therefore, the direction is the same. So in order to encapsulate the concept of just a change in direction and strip away the magnitude information, so to speak, in this derivative, that leads to the concept of what we call the unit tangent. And that's one of the important unit vectors that we'll talk about in this chapter. So let's stay tuned for the second page, for the next page, for a definition and more examples. All right, so definition here, the unit tangent at t for a vector function r bar of t. Remember how we make a unit tangent. Unit vector means, remember, magnitude, as the name implies, magnitude 1, right? Tangent is a vector. Take any vector, you want to make it of length 1, you scalar multiple by 1 over its magnitude. So the notation for it is t of t, t bar of t, which is going to be 1 over the magnitude of r prime of t, scalar multiple with r prime of t. Via an abuse of notation, just to make things much clearer, we're going to typically write down that the unit vector, the unit tangent t of t is just r prime of t divided by its magnitude. But division doesn't exist. Remember, by division I mean scalar multiplication by the reciprocal by the reciprocal of that magnitude. And remember, the reason, I mean the indication or the use of this is a vector that indicates the change in the direction of motion, irrespective of speed, right? So if you want to track just the change in direction, then you're looking at the unit tangent. Now, needless to say that if you can always multiply a unit tangent by the speed, then you get, of course, you recreate the velocity. I mean, excuse me, the velocity to begin with, right? So you could always separate the magnitude and the direction via this tool. And obviously, the notation for the unit tangent is t bar of t. Now, remember, this comes from a derivative, right? So let's go over an example. Sometimes there is a bit of a confusing part later because there will be another vector which comes from differentiating t, but t itself comes from a derivative. But we'll get to that when the time comes for the next lesson. So let's compute the unit tangent for an example. So let's say r of t is equal to the vector t ln of t, and let's say t greater than 0, so we don't have any worries with the domain there. Tangent vector will be obviously 1 over t, In order to compute the unit tangent, I'm going to have to compute the magnitude of the tangent vector, which is square root of 1 plus 1 over t squared. And then finally the unit tangent in this case will be, let's write it like that, 1 over the magnitude. I'm going to add up these two fractions there, so that's going to be 1 plus t squared over t squared under the radical, scalar multiple with 1 over t. Let's clean it up a little bit. I can take t out of the radical, so that's t over square root of 1 plus t squared, scalar multiple 1 over t. Usually we can leave this outside this scalar if we don't have any reasons to bring it in, but depending on the case or your preference, you can bring everything into a single vector. T cancels and we have the unit tangent at t. I'd like to point out that computation of these vectors can be quite tedious. So if you have to do it by hand, you have to be smart and make sure you plug in an actual value if that's the question as soon as possible. Now, if the question is to find these vectors at any time t, then you're out of luck. I mean, you just have to do the computation either by hand or with Maple or something similar. But here's another example. Let's say I give a vector, let's do this one in 3D, right? So let's say we have a vector of coordinates t squared minus 2t, 1 plus 3t, t third over 3 plus t squared over 2. And let's say I want the unit tangent at the point 2. All right, so let's go over the steps here. So obviously I have to differentiate with respect, I cannot plug in 2 right away, right? I need to differentiate with respect to t, so I can find the unit, the tangent vector. That'll be 2t minus 2, 3 t squared plus t. But notice that if you want to compute the magnitude right now, there's no need to do it before plugging in 2 for t, right? Because there is no more differentiation to do at this point, right? I mean, I just have to compute the unit tangent at the point t equal to, not at any point in general. So I'm not going to bother to compute the magnitude in terms of t, which will be kind of a tedious part, right? I'm going to just go right away and set up that the unit tangent at 2 will be r prime of 2 over the magnitude of r prime of 2. So I'll just plug in 2 right away. 2 times 2, 4 minus 2, that's 2, 3, and 6 over the magnitude of r prime of 2, which is square root of 4 plus 9 plus 36. That becomes 1 over square root of 49, which is 1 over 7. Scalar multiple with 2, 3, 6. You can leave it like that, or you can bring in the scalar inside the vector itself. You will see later we're going to talk about something called the normal to the curve. That's really tedious because that requires a differentiation of t, of the unit tangent itself, and I usually do that with Maple, or if I put it on exams on paper, I make it so that it can simplify easily. Speaking of which, let's see if I find a quick example. Be aware of quick simplification. So for instance, let's say my vector is cosine of t, sine of t, and t. And let's say I want t of t, right? I mean the unit tangent. Not at a specific point, but at any point. So let's say r prime will be minus sine of t, cosine of t, and 1. But the magnitude of r prime, it's not that bad actually because of trigonometric formulas, right? So if I square these guys, I get sine squared of t plus cosine squared of t plus 1 squared, and this happens to be 1, so it's not that bad, right? It's square root of 2, which means altogether the unit tangent in this case is just 1 over root 2 scalar multiple with r prime. So let's see, there is one more. We're going to get to the integral in a minute, but I mean, for the integral we're going to spend just one example, but before we do the integral of a vector function, which is defined in a very analogous way, just like in calculus 1, let's go over another definition, another geometric concept, which is the so-called angle between two curves, and that'll be on the next page. All right, so the concept of an angle between two curves, I wouldn't say it's extremely important. Some of these concepts are not going to be used so often in the class, but it brings an interesting point of conversation that I really like to emphasize when I teach this in class. So just like we defined the angle between two planes via vectors, stands the reason that if two curves intersect, there has to be a way to measure the how far apart they are at the intersection point. So that's roughly the main idea, right? So let's say we have two curves, space curves, right? And let's see, let me make a picture here. Again, I'm going to overly simplify the picture so that I can sketch my vectors here easily, that the vectors that I'm going to need. So let's say this is the intersection point, and hold your thought for a moment, because it'll be obvious immediately why I did this, but I'm gonna actually denote these curves with a different parameter. By the way, let me actually write down the quick definition right away. So the angle between two curves is defined as the angle between the tangent vectors at the intersection point. Now obviously the curves could intersect in more than one point, but at each of these points you can talk about this concept of the angle between the curves at that point. So it's still a local property. So right off the bat, we already mentioned here the definition in the sense that it's going to be the angle formed by these two tangent vectors. So I'm gonna write an example right away, right? So the two curves in question, let's call them R1 and R2, but I'm gonna use a different parameter for both of them, and you will see in a moment why that's the case. So R1 of t, let's say that corresponds to this one here, is made of the components, let's see, t, 2 minus t, and t squared plus 1. And R2 of s, which is the second curve here, is made of the components 2 minus s, 2s plus 1, s squared plus 9. Now you should pause for a moment, because this is a nice question to ask, and I usually ask it in class. Why do you think I need to use two different notations for the parameters? Because remember, first of all, I have to figure out where the two intersect, right? And then compute the tangent vectors, and then find the angle between them with one of the formulas we learned before. But why can't I use t in both cases? So pause for a moment and think about a couple of minutes, maybe even 5 minutes. It's worthwhile to think about why I cannot use the same t, like the same parameter notation for both curves. All right, so The reason is because if you again make the analogy of motion in space, if I use the same variable, it's like I'm watching, for example, a motion in both of these curves. Let's say we have two mobiles, right, that move on these curves. If I use the same chronometer, it's like I'm watching two mobiles that, although they move like two mobiles, one on a curve. Oops, I'm gonna close this. All right, sorry about the interruption. It's kind of embarrassing, but I cannot actually cannot have that turned off. So let's go back to what I was saying, right? The reason why we have two different parameters. So if you imagine that you measure two mobiles moving on the curves, on the two curves, although they may intersect these two curves, the mobiles may not actually meet each other because they may arrive at different times. So remember, each of these vector functions describes the motion of a mobile on the curve. And it doesn't have to be, and usually it's not the case that the motion, the intersection happens at the same time. So we can actually write this in words to make it clear. The intersection may not happen at the same time for both mobiles. Again, if we use the analogy with mobiles on the curve. So when we figure out the intersection point, it shouldn't be a surprise that the intersection points corresponds to different parameter values. Although it's the same geometric point, different parameter values for R1 and R2. And we can convince ourselves immediately that that's the case. How do we find an intersection point? Well, we're going to set up the two vectors equal to each other to see if they intersect at a given point, right? So we set up t to be equal to 2 minus s, 2 minus t equal to 2s plus 1, t squared plus 1 to be equal to s squared plus 9. Now notice there are three equations and two unknowns. Typically, if the two curves intersect, you can just pick any two equations, solve for s and t, and just double check that the third equation also matches, right? I mean, if it doesn't, that means that the curve may not intersect, right? But if they do intersect, all three equations will be satisfied for a pair of parameter values. So let's just take the first two equations and manipulate the terms a little bit. S plus t is 2. 2s plus t from the second equation should be 1. If we subtract the two, we get s minus 1. And then if we plug it in back into t, 2 minus s, then the parameter value is 3. So R1 of 3, right, t equals 3 for R1, and R2 of minus 1 would indicate the intersection point. All right. So let's proceed with finding the angle between them. We need the tangent vectors at these points. So let's find the tangent vector. It's the tangent vector for any time t, and then plug in the parameter. So R1 prime of t is going to be 1 minus 1. So check here on the corner here. Differentiate 1 minus 1 2t. And then at the parameter value 3, this becomes 1 minus 1 and 6. Second curve, R2 of s, R2 prime of s, differentiate, that's minus 1, 2, and 2s. And at parameter value minus 1, that becomes minus 1 to negative 2. So let's find the angle between them. Let's call it theta using cosine formula. R1 of 3 dot 2 r1 prime of t of 3 dot r2 prime of minus 1 over the magnitude of these guys. Alright, so what is the dot product? 1 times minus 1 times 2, 6 times minus 2. Magnitudes are 1 plus 1 plus 36, 1 plus 4 plus 4. I checked this ahead of time. Check it yourself with the calculator. Use a trig inverse cosine, right, of this quantity. This should be equal to 144 degrees. Approximately 144 degrees. All right, so finally in the last page of this lesson, we're going to talk about integrals of vector functions. We're going to spend a bit less time because, again, the concept is quite analogous to calculus 1. It's just going to be integrals by component. So stay tuned for the last page. All right, so without further ado, integrals of vector functions. They follow the same concept as in calculus 1, or analogous to what we did before. It's going to be the same concept by components. So let's start again with a vector functions with components a of t, b of t, c of t. We're going to define the integral of r of t dt as the vector made of the integrals of a of t dt, b of t, c of t. Same thing for the definite integral. I'm not going to rewrite the whole thing all over again. Well, maybe we should just write it just to make it clear. Let's say you want to have the integral from I cannot use a and b. Let's say from m to n of r bar of t dt. That's going to be basically the component, the vector with the same integrals for each component function. So, going over a couple of examples, let's see, we're gonna go over examples maybe in R2 just to save some time. Obviously it's like doing three integrals instead of one, right? If you have one in R2, right? So let's start with the definite integral. So let's say I want to compute the integral from 0 to 2 of the vector functions t e to the t squared. I should mention here, I don't do this often because I don't, if I don't need to, I kind of prefer this component notation. But another notation, another way, remember, to denote this is via the standard basis, like ti plus not e to the t squared. Here I meant t to the t squared, the second component. Right? You can write the same thing via standard basis, right? It's the same idea. Whatever you're going to get for the integral from 0 to 2 of t, that's going to be your times I, and then whatever you're going to get for the second integral, that's going to be j times j. So using this notation, this is going to be the integral from 0 to 2 t dt, integral from 0 to 2 t to the t squared dt. You can write both integrals at the same time. If you can, if it's necessary, if one of them is more complicated, you can take it separately and compute it. The first one is immediate, right? It's t squared over 2. This one requires a u substitution. Take u to be t squared, du is 2t dt. and then the new bounds of integration, I always require changing the bounds. If t is 0, u is 0. If t is equal to 2, u becomes 4. And you can keep on going with both components at the same time, right? So t squared over 2 evaluated between 0 and 2. And let's do it in 2 stages. The second one becomes the integral from 0 to 4 e to the u times 1 over 2 dt, du, right? T dt becomes du over 2. And first one becomes 4 over 2 minus 0. Second one is 1/2 e to the u evaluated between 0 and 4. And then finally the integral becomes 2 2 and e to the 4 over 2 minus 1/2, right? E to the 0 is 1. So e to the 4 over 2 minus 1/2. Be aware that if you compute an antiderivative, in other words, an indefinite integral, you always have a constant of integration which is a vector. So for an antiderivative of a vector function, constant of integration becomes a vector, right? So let's go through an example of this kind. So let's say I want to compute the integral of t cosine of t, right? I don't specify any bounds. So the idea is that yeah, so I mean we can actually illustrate this maybe with an extra step here. When you translate the integral by components, each of them has a constant of integration, right? After you solve the integral, you know, a constant of integration here, a constant of integration here, but you can take it out and put it together into just a constant of integration vector, because usually that's a little bit easier to handle, especially if you have then an initial value of some sort that will give you what that constant of integration is. So for example, let's say what I got is r of t, right? So let's say r of t is this integral, and then I compute the integral by components. So this will be t squared over 2 integral of cosine, which is sine of t, and then the constant of integrations together come up in this constant vector c bar. And let's say you know, I provide that r of 0 is equal to the vector 3 and 5. So once you compute the antiderivative, then of course you can compute c using this information after you compute the integral, right? So you plug in 0 for t, which is kind of not that complicated, right? Because there's going to be 0 sine of 0, 0 plus c bar equals 3, 5, right? So the constant of integration becomes 3, 5. You go back to the original and plug in back the constant of integration, which is this vector 3, 5, and then of course you can bring everything into a single vector. This won't happen that often in this class, and I don't insist too much on it because it's really calculus 1 stuff done for each component. So it should be very familiar to everybody at this point when you take this class. With the only difference is that you use vectors and it's everything by component. Things won't be the same obviously for other integrals of other types of functions later on. That's a whole different matter. But to conclude, derivatives and integrals of vector functions, in essence are derivatives and integrals of each component of those vectors. So with that, that's it for today, and I'll see you next time.